Lesson 7 is on integrating factors. Integrating factors in order to transform equations into exact equations. I'm Ronald Johns. We will answer these questions and more. What are integrating factors? How do we find them? And how do we use them to solve these differential equations? Suppose we have the differential equation m of xy dx plus n of xy dy equals 0. That is not exact. Can we find a function mu of x such that the equation mu of x times m times dx plus mu of x times n times dy equals 0? Can we find a mu of x such that this equation is exact? If we can, this function mu of x is called an integrating factor for this equation up here. We change an equation that's not exact into an equation that is exact by multiplying both sides of the equation by some function mu of x. How do we calculate, how do we find such a function mu of x? As an example of using an integrating factor, let's look at this problem. Let's consider the ordinary differential equation 2 cosine y dx minus x sine y dy equals 0. This is of the form m times dx plus n times dy equals 0, where m and n are functions of perhaps x and y. First, let's determine if it's exact. If you take the partial of m with respect to y, it turns out to be minus 2 sine y. If you take the partial of n with respect to x, it turns out to be minus sine y. These are not the same function, so the ordinary differential equation is not exact. But note that if I just multiply both sides of this equation by x, we get 2x cosine y dx minus x squared sine y dy equals 0. And this equation is exact. We saw that in the previous lesson. And also, this equation is equivalent to this one over here. All we did was multiply both sides by x. So as long as x is not 0, I guess, they are equivalent. So mu of x is the function just x, is an integrating factor for the current problem. It takes an equation that is not exact, transforms it into an equation that is exact, and we know how to solve exact ordinary differential equations. Let's continue to look at the differential equation given here. We saw that it's not exact, and we saw that mu of x equals x is an integrating factor that will make it exact. If we didn't know about this integrating factor, how would we find it? Well, in that case, we would want to multiply this equation both sides by mu of x and have the resulting equation turn out to be exact. If we multiply both sides by mu of x, we have this. And now, this is an equation that we can solve for mu of x in terms of the other stuff here. And we're going to solve for it by requiring exactness. So if I look at this function here, think of it as m of xy. Think of this function over here as n of xy. The partial of m with respect to y turns the partial of this factor right here with respect to y just turns out to be minus 2 mu of x sine of y. The derivative of the cosine is minus the sine. Similarly, if we differentiate this n with respect to x, after a little bit of a calculation, we find out that it's equal to this. In this case, since we're differentiating with respect to x, we have a function of x times a function of x here. Sine of y basically is treated like a constant. But in any case, to differentiate this, we need to use the product rule, and this is what we get. Okay, so then to be exact, we need these two things to be equal, which means this stuff here has to equal this stuff here. Notice that in this equation we have a factor of mu of x, and in this equation we have a term that has a factor of mu of x and another term that has a factor of mu prime of x. We want to solve this equation. So we just saw that the partial of m with respect to y equals the partial of n with respect to x, if and only if this holds. We can simplify that a little bit. Notice that we have a mu of x sine y term here. On the other side of the equation, we also have a term involving mu of x sine y. So we can combine those two on the left-hand side. So our differential equation will be exact if minus mu of x sine y equals minus x mu prime of x sine y. Okay, so in that case we have that x times mu of x has to equal mu of x, dividing both sides of this equation by minus sine y. This can be written as mu prime of x over mu of x equals 1 over x. Integrate both sides with respect to x. That's what we did here. This left-hand side is the log of mu of x plus an arbitrary constant. The right-hand side is log of x plus an arbitrary constant. Combine the two arbitrary constants into one arbitrary constant on the right-hand side. So we have that log of mu of x equals log of x plus c. Take exponentials of both sides, and we can write the equation as mu of x equals e to the c times x. C is an arbitrary constant, so e to the c is basically an arbitrary positive constant. So mu of x is an arbitrary constant times x. If I let a be 1 here, then mu of x equals x is an integrating factor for the ordinary differential equation. I could have used other constants also. 2x would be an integrating factor, pi times x would be an integrating factor, any constant times x. So we once again, by multiplying by that integrating factor, we end up solving 2x cosine y dx minus x squared sine y dy equals 0 again. And we saw earlier in this lecture that the general solution to this ordinary differential equation is x squared cosine y equals c. So the question we have is, how do we find an integrating factor if one exists? Let's look at this problem. That ordinary differential equation we just considered, 2 cosine y dx minus x sine y dy equals 0, is not exact. Find an integrating factor mu of x, a function of x, that makes it exact. Okay, so what we want to do is the following. We want to multiply both sides of this equation by mu of x, so that we get 2 mu of x cosine y dx minus x mu of x sine y dy equals 0. And we want this to be exact. So we want the partial derivative of this with respect to y to equal the partial derivative of this with respect to x. And hopefully that will allow us to figure out what the mu of x has to be if such a mu of x exists. So if I first find the partial of m with respect to y, this thing, that's the derivative, partial derivative with respect to y of 2 mu of x cosine y. And since we're differentiating with respect to y, 2 mu of x is treated like a constant. The derivative of cosine y with respect to y is minus sine y. So this derivative is just minus 2 mu of x sine y. On the other hand, if we look at the derivative of n with respect to x, partial derivative, that's the partial derivative with respect to x of this stuff over here, minus x mu of x sine y. And when you differentiate that, you get minus mu of x sine y minus x mu prime of x sine y. Why do we get these two terms? Well, if you look at this, we have a product of functions of x here. so we had to use the product rule. So the partial of m with respect to y equals the partial of n with respect to x, if and only if this thing over here equals this stuff down here. And that's the equation that we have at the bottom of this slide. So far, we have seen that if mu of y is an integrating factor for our ordinary differential equation, then we had to have it satisfying this equation right here. Well, this had to be 0, had to satisfy this equation right here, which turned out to give us this on the last transparency. Let's get mu prime and mu on one side of the equation and the other stuff on the other side. So our differential equation will be exact if 2 mu prime over mu equals sine of y over cosine of y. Then we'll integrate both sides of that with respect to y. Also, I guess, multiplying both sides by half. So we get this. Mu prime of y over mu of y dy integrated is log of absolute value of mu of y plus the constant, arbitrary constant of integration. Similarly, the integral of sine of y over cosine of y is equal to minus the log of the cosine, absolute value of the cosine of y. In our calculation here, I'm just going to look at the one case where the log of mu of y equals minus the log of the cosine of y. So integrating both sides of this equation, we get log of mu equals minus 1/2 log of cosine of y plus an arbitrary constant of integration, which is equal to the log of 1 over the square root of cosine of y plus a constant of integration. Using the fact that we have these more general formulas, we have some extra cases to look at and some extra level curves to graph, but I'm not going to worry about that. If you're interested, you can work out the details. So anyhow, taking exponentials of both sides of this equation gives us that mu of y is equal to e to the c times 1 over the square root of cosine y. And we may as well pick this constant to be 1. Any multiple of an integrating factor, any constant multiple, is still an integrating factor. So we can use mu of y is 1 over the square root of cosine y. And then if we look at the differential equation that we started with, multiplying both sides by that integrating factor, we get this equation down here. So let's continue the solution of our problem. At this stage, we want to solve the equation 2 times the integrating factor, 1 over the square root of cosine y, times cosine y dx, minus x times the integrating factor, times sine of y dy equals 0. Okay, so let's just algebraically simplify this a little bit. Here we have cosine y divided by the square root of cosine y, which gives us a factor of the square root of cosine y, and we have that factor of 2 in front and also the dx. The second term we have for a numerator for this product minus x times 1 times sine y, so that's minus x times sine y, divided by this denominator, square root of cosine y, times dy equals 0. Okay, and this should be exact, and so what we want to do is to find a function f of xy, such that this equation is going to be the partial of f with respect to x dx plus the partial derivative of f with respect to y dy equals 0. So that means that the partial of f with respect to x has to equal 2 square root of cosine y. That's what we have right here. Integrating this with respect to x, treating y as a constant, we get f of xy is 2x times square root of cosine y plus an arbitrary function of y. This more or less plays the role of an arbitrary constant when we're looking at anti-differentiating partial derivatives. Okay, so f of xy is equal to this. What we need to do is to find out what this h of y is so that we can find the solution to our differential equation, our exact differential equation. So let's use the fact that we also know that the partial of f with respect to y has to equal n of xy. And so the n of xy is this stuff up here, which we simplified to this stuff over here. So the partial of f with respect to y is minus x times sine y divided by the square root of the cosine of y. Okay, but on the other hand, we also have that the partial of f with respect to y is the derivative with respect to y of f, which is this stuff right here. So we'll just plug that in. And now we would differentiate this term by term, okay? And so we get, what do we get here? We're differentiating with respect to y, right? So here we more or less have a constant times cosine of y raised to the 1/2 power. So the derivative of this term is going to be that constant 2x times 1/2 cosine y to the minus 1/2 power times the derivative of the cosine of y. And that gives us 1/2 minus sine y over the square root of cosine y. Differentiating h of y with respect to y just gives us h prime of y. So what we have here with a little bit of simplification is the partial of f with respect to y equals this stuff, and this simplifies a little bit because we have factors of 2 in both the numerator and denominator. So this becomes minus x sine y square root of cosine y plus h prime of y. Okay, but we already know that the partial of f with respect to y must equal this. And so the only way that the partial derivative of f with respect to y can equal this, and also all of this, is if this h prime of y is 0. And so we can choose h of y to be 0 to satisfy this. So then f of xy, coming back here, is going to be 2x squared root of cosine y plus 0. And so that's what we have here. And f of xy is 2x times the square root of cosine y. So what we found is that when we use this integrating factor, mu of y is square root of cosine y, then we get implicit solutions to this exact differential equation of this form. 2x times the square root of cosine y equals c. Okay? Now, we have to remember that in order to get this solution, we had to make the assumption in our calculation that the cosine of y was not a negative number. And so this is only going to give us solutions in that particular case. In our differential equation that we considered, when we used mu of x equals x as our integrating factor, we got implicit solutions that look like this. X squared times cosine y equals a constant, where this constant could be any number. When we use the integrating factor mu of y is 1 over square root of cosine y as our integrating factor, we got implicit solutions like this. 2x times the square root of cosine y equals c, where c is an arbitrary constant in this equation. It's an arbitrary constant in this equation that more or less is giving us something like general solutions. By varying the constant, we can get a whole family of solutions to our exact differential equation. These two values of c are not necessarily the same to give the same curve, the same solution in both cases. C is an arbitrary constant. Okay, so we could ask ourselves, do these really generate the same family of solutions? So to answer that, we would look at the level curves for x squared cosine y and also for 2x cosine y. Okay, by using SageMath, we can plot these implicit solutions by using a function called contour plot. This graph here is a contour plot of 2 times x times the square root of cosine y, where x goes from minus 12 to 12, y goes from minus 12 to 12. Fill equals false just means that there's no shading in here between these level curves. On this side, we have a contour plot of x squared times cosine y, also x going from minus 12 to 12, y going from minus 12 to 12, with no extra shading added. And if we look at these, in this first picture, this first graph, it looks like something is missing compared to the second one. And why would this happen? Well, remember that when cosine of y is negative, the square root of that is not going to be defined as a real number. It would be an imaginary number. So we're missing some plots in here that do appear on this side. So what we're getting basically over here is a subset of all of the solutions to that differential equation. So when we multiply by integrating factors, we have to be careful, because when we write that integrating factor down, like 1 over the square root of cosine y, it might not be defined for all values of the variables x or y that come into play. And so you might be missing something. But let's see if those two solutions can give us a curve in common. So let's consider the level curves for 2x times the square root of cosine y. And I'm going to look at the particular case where that equals c, and the c that I'll be using is 3. 2x squared root of cosine y equals 3. Okay, so if we have a curve gamma, which is going to be the set of points x, y satisfying this equation, then for any point x, y on gamma, those coordinates would have to satisfy this equation. So let's square both sides. And so this squared equals 3 squared, which is 9. If we square this stuff, we're going to get 2x quantity squared, which is 4x squared. And when you square this factor, you're going to get, when we square this factor up here, squaring the square root, we just get cosine of y, and so that equals 9. Dividing both sides by the 4 gives us x squared cosine y equals 9/4. So one of the level curves of the function 2x squared root of cosine y is also a level curve for x squared cosine y. Okay, so what we have is that curve gamma that went through the point where that constant was 3 also is a level curve for this function, because it's on this level curve, which basically is equivalent to this one in this case at most points except where the cosine of y is negative. Okay, so the set of level curves 2x squared root of cosine y equals c is a proper subset of the level curves x squared cosine y equals c, using mu of y equals 1 over square root of cosine of y as our integrating factor. We would miss some implicit solutions to that differential equation because we were adding an extra condition to y. cosine of y had to be positive in order for this fraction to be a real number. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.